Moving on to the next section, we're going to do two sections today, 7.2 and 7.3. We're still going to talk about things that have exponents, and we're going to talk about the different rules that come with items like bases that have the same bases or different bases, and what kind of rules we can apply with the exponents. So the only rules we've learned about is in 7.1, we've learned about exponents that have been 0, so those have been dealt with, and we've learned about exponents that have been negative, and those have been dealt with. So today what we're going to do is talk about multiplying powers of the same base, and then we're going to talk about some more multiplication properties of addition. Alright, we can do the got it, but we can do that in class if we want to. As we move down, I had the wrong paper, there we go. As we move down, I did give you the same table I gave you yesterday. We've already talked about the power of 1. You've talked about that a long time ago. We talked about the power of 0 yesterday. We talked about the power of negatives. Today we're going to talk about items that look like these. Okay? And I know it looks like we're going to talk about a whole bunch of different types, but those are all kind of very similar one to another. Okay? So let's move on and just kind of teach it to you as we move along. The first essential understanding is that you can use a property of exponents to multiply things with the same base. Please highlight the word same base or circular or whatever, because that's going to be important. For example, do you see how this is 3 to the 4th and 3 squared? That equals, that's an equal sign there, that equals a whole bunch of 3's, right? It equals 1, 2, 3, 4, right? Times 1, 2 of them. Because the 4 came from the first and the 2 came from the second. Now another way of writing that is simply 3 to the, now that had four of them, right? There's 4 here and there's 2 here. That just means you have 3 to the 6th power. So what that means is that you are allowed to add their exponents if you have the same base. So in terms of a general algebraic equation, if you have the same base, a and a, you may add the exponents together, and then it's simplified. You can work with it together like that. Moving on to problem 1. What is each expression written using a base only once? Well, you see how they're the same base, 12 and 12? We just add their exponents, 12 to the 7th. We're not going to evaluate that, we're just going to rewrite it. Now this rule is going to get complicated when we get to another rule, so really memorize that if the base is written separately, we add. Can you write that down? If the base is written separately, then you add the exponents. Okay? Now, in the next problem, I know it's hard to see on your paper, but it's -5 to the -2 and -5 to the 7. So, we get -5, put it in parentheses because it's negative. -2 plus 7 is a +5. Okay? We can do this on the got it. Why don't you go ahead and do them, pause the video, do them quickly, because I'm going to go over them quickly and see if you get them right. This one we get 8 to the 9th, because 3 plus 6 is 9. This one we get 0.5 to the 5th, because excuse me, I said that wrong, because that's a -8. You get 0.5 to the -11th, because -3 and -8, that's what that is, makes -11. And the last problem, you have -3, 2, and 6, all with a base of 9. So you get -1 plus 6 is a +5. Okay, moving on. So that's how you handle problems like that. As we move on, you are going to see how we multiply powers in algebraic expressions. It's going to be the same type of idea, okay? Look at part A. The only thing that has similar bases is the z to the 5th and the z to the -12. When we read the directions, it says, what is the simplified form? Understand that simplified form means no negative exponents in the final answer. Okay? That's not allowed. Okay. So what I'm going to do is I'm going to kind of rewrite this as 4 times 9 z to the 5th, z to the 12th. Since multiplication is commutative, I can rearrange it. Okay, 4 times 9 makes 36. They didn't have any special exponents, so you can just multiply them together. And you add the exponents of the like, or the ones with the common base. So 5 and negative 12 makes negative 7. Okay, part B. I see that a and a squared can be put together. I'm going to rewrite this, putting kind of my like terms next to each other. 2 times 9 times a squared times b to the 4th. I can do that since multiplication is commutative. The 2 and the 9 become 18, plain and simple because they don't have anything special properties to them. The a and the a squared become a to the 3rd because 1 plus, there's a hidden 1, 1 plus 2 makes 3, and b to the 4th stays b to the 4th. Okay. Oh, I completely neglected the 3. Did you see that? That was special of me. Put a 3 on there too because of that 3. I apologize, I missed it. So we have to do 2 times 9 times 3. I wonder who caught that. 2 times 9 times 3, that makes 54. I apologize for missing that. Alright, moving on. You can try the got it's on your own and then come back and watch a video and see how you do. We have an x to the 4th and an x to the 9th and an x. And we have 5 and 3. I'm going to rewrite them. You don't have to rewrite them, but since this is the first time you're learning it, it's probably a pretty good idea if you do. We have 4, 9, and 1. That makes 14. So we have 15x to the 14th. Part B, C, and C. The negative 4, the 7, and the 2 can be multiplied together. Alphabetically, I'm going to write the C's next, and then the D's, and then final answer, negative 4 times 7 times 2 is negative 56. C to the 3rd and C to the negative 2 makes 1C, or C to the 1st, and then it's D squared. Remember, if we would have ended up with a negative exponent, it would have had to have gone on the bottom. You might want to write that and pause the video and write that down. If we would have ended up with a negative exponent, it should have gone to the bottom. We're going to see that happen in part C. The only number or coefficient I see is the 12. I see a j squared and a j. I'll put those together. And then I see a k to the negative 2. So I rewrote it. I get a regular 12 and I get j to the 3rd. Notice what I do to k. You remember how we're not supposed to have negative exponents whenever we simplify? You move it to the bottom and you get k squared. Alright. So simplified form is what they asked for. See how it asked for the simplified form? That means no negative exponents, which is why I had to fix this one at the end. Explain how to simplify the expression x to the a, x to the b, x to the c. Well, you write the common base once, and you would add the exponents. And since they're variables, we just rewrite it like that. Okay? Now we're going to apply this concept to scientific notation. Applying it to scientific notation, let's go ahead and actually read the problem that we're given. You can use the property of multiplying powers in the same base to multiply numbers written in scientific notation. Recall that you use powers of 10 when you make really big numbers and really small numbers, especially in science, right? And that makes them more convenient. In scientific notation, you can write any number as a to the 10 to the b, where a is between 1 and 10. In other words, it has to be like 1.2, 2.2, 3.1, 9.9. If, for example, 256,000 can be written as 2.56 times 10 to the 5th. This is something you've learned over and over and over again in middle school. You'll see it repeated through high school, so hopefully you kind of got a nice grasp on that. So let's see what we can do on problem 3. At about 20 degrees Celsius, 1 cubic meter of water has a mass of about 9.98 times 10 to the 5th grams. Every single gram, or each gram, of water contains about 3.34 10 to the 22nd molecules of water. About how many molecules of water does the droplet of water shown below, how much does it contain? All right, let's go ahead and get started on this problem. We are told that we need to find out how many molecules of water a single droplet has. So you're going to do some conversion. I'm going to try to make this look like your science class, okay? So we need our final answer to be in molecules. Move that over. There you go. So we're just going to set up a nice little chart, try to work things out, okay? Well, let's see what we know about molecules. They tell us that there are 3.34 times 10 to the 22nd molecules in every gram. And I see that from this sentence because it says in each gram. But if we look at what we're given cubic meters. Well, that's not a molecule or a gram. So we have to use this other sentence that says 1 cubic meter has 9.98 times 10 to the 5th grams. So I need 9.98 times 10 to the 5th grams to be on the top because G and G will cancel. See how molecules, I put molecules on the top so it will end up being there. Now remember, that was this many grams in 1 cubic meter. Okay? We also know in this problem, I need another times symbol here, that for this particular problem, the droplet of water that's given to us is 1.13 times 10 to the negative 7 cubic meters. So we have everything set up. Look how the cubic meters cross off as we go along, because I think you should know when something's on the bottom and something's on the top, you cancel them out, like the grams and the grams, the cubic meters and the cubic meters. Please notice in my problem, the only unit that we have left is molecules, which is good because that's what I need at the very end. Now let's go ahead and do some math with this. I hope you guys see this one has a 10 to the 5th, this one has a 10 to the 22, and this one has a 10 to the negative 7. 5 and 22 makes 27, with a negative 7 makes 10 to the 20th. Since 10 had a common base in each of these, I can put them together. The next thing I'm going to do, grab my calculator, can't do this in my head, and do 9.98 times 3.34 times 1.13, and I get 37.7 essentially. Now, that is my answer, but I hope you know that this is not proper scientific notation. I need this to be 3.77, not 37.7. Now, if I move the decimal one more place to the left, and this is already positive, that's going to make that times 10 to the 21st. And that's how many molecules are in that single drop of water.